Welcome to lecture 20, where we introduce a new idea, the idea of subsequence. Let AN be a sequence of real numbers. A sequence BK is a subsequence of AN if there exists a strictly increasing sequence nk for k larger than or equal to 0 such that bk is equal to a and k. So in other terms, what we are saying is that the elements of bk, the elements of this subsequence, are nothing else than elements that belong to the original sequence an, which are anyway picked from a strictly increasing sequence of indices. So let's try to visualize this. Let's say that this is A0, A1, A2, A3, A4, A5, A6, A7, A8. So this is the original sequence AN. And now we cherry pick some elements of this sequence. For example, we pick A0, then we pick A2, A3, and then A5, and then A7. Okay, so we are basically picking elements, but we are picking these elements in a specific way, always jumping forward. Okay, always jumping forward. What we are not doing, we never do this. We never, for example, from A3 jump back to A1. Okay, we don't do this. So we basically always select the next element moving forward in the sequence. Now, this is just like saying that these elements that we have checked, they belong to a new sequence A and K, such that N0 is equal to 0, N1 is equal to 2, N2 is equal to 3, N3 is equal to 5, N4 is equal to 7, right? So, well, the first element, A0, that we have selected, this is basically B0. This is B1. This is B2. This is B3. This is B4. So you see that we have this sequence of NK, which is strictly increasing. In fact, if we rewrite NK, the sequence NK here, we have 0, 2, 3, 5, 7. And we clearly see that this sequence is strictly increasing. So if this is the sequence of the indices, the sequence A and K would be basically A0, A2, A3, A5, A7. But this sequence is exactly what we call BK. So this will be B1, B2, sorry, this will be, let me start from B0. B0, B1, B2, B3, B4. Okay, so the idea is exactly this. We start from a sequence AN and we go and pick some elements, but we pick these elements in a specific way, always selecting an element that is ahead of the previous one, never before the previous one, which is just like saying that the sequence of the elements, the sequence of the indices of the elements of a n that we pick is strictly increasing. This sequence of elements will make up exactly the subsequence. Now, let's give some example, okay? Let's give some example of a so typical examples of subsequences. We have even numbers. So we go and select just the element of the original sequence that have indices which are even numbers. So we have in general a to the 2k, which means a0, a2, a4, a6, a8, and so on and so forth. And once again, we see that the sequence of the indices 0, 2, 4, 6, 8 is an increasing sequence. Odd numbers, a to the 2k plus 1. We have a1, a3, a5, a7, and so on and so forth. Or square numbers, like, so that means a to the k square. So we start with a0, then we have a1, then we have a4, then we have a9, and so on and so forth. So these are just examples of subsequences taken from the original sequence. Now that we know what a subsequence is, we can state the following important theorem. Let bk be a subsequence of an. Then, if an tends to L into the extended real line, meaning that this L can be a finite real number or can be plus or minus infinity, then the subsequence bk will tend to the same limit L into the extended real line. Okay, let's give a proof of this, which is quite straightforward. Okay, by hypothesis we know that an tends to L into the extended real line, and now we just re-express this by just using the definition of limit. This implies that for every epsilon larger than 0, there exists an n0 into the natural numbers, such that for every n larger than or equal n0, we have that an minus L in absolute value is less than or equal to epsilon. Now, this last definition is valid if L belongs to the real numbers. Let's suppose that instead L is plus infinity. Well, in that case, we can say that for every m into the real numbers, there exists an n0 into the natural numbers, such that for every n larger than or equal to n0, we have that an will be larger than or equal to m. And finally, if L is minus infinity, then we have that for every m into the real numbers, there exists an n0, such that for every n larger than or equal n0, we have that an will be less than or equal to m. So The thing is that in each of these three cases, we have some condition, which could be this one, or this one, or this one, that they are verified definitively. So what really matters for us is that this is happening when n is larger than or equal n0. So we can write this down. We can visualize this on the real line. There will be at some point an n0, and we know that if we exceed, if we go beyond this n0, for every n larger than this n0, the condition is verified. Okay, so but now let's make some consideration about bk. So what we are saying is in general, if I pick an element k that is larger than or equal to n0, we know that for that index k, the previous conditions are verified. Okay, just to be to make the proof simple, let's consider the first situation where we have a real limit. Okay, so we are saying that if k is larger than or equal to n0, certainly we know that ak minus L in absolute value will be less than or equal to epsilon. And you can see that a similar statement can be done for the case of a diverging sequence. Okay, but now we know that bk, which is the subsequence, is just a to the nk, right? And we know that nk is an increasing sequence. So what we can say is basically that in this nk will be certainly larger than or equal of a n0, just because we know that for every k larger than or equal n0, a nk will be larger than or equal n0. Right? So because this is an increasing sequence. Therefore, we can conclude that the absolute value of a nk minus L will be less than or equal to epsilon, which is just like saying that bk minus L in absolute value is less than or equal to epsilon, which finally proves the fact that bk will tend to L. And this concludes the proof. Now, it is important to realize something, that this theorem is based on the hypothesis that the original sequence AN has a limit, L. Now, this limit can be finite or can be infinite. Anyway, has a limit. If this is the case, if AN tends to a limit L, we know that each subsequence extracted from AN tends to the same limit. But if AN does not have a limit, well, it is possible that the subsequences have totally different behavior. So let's make a note. If AN has no limit, bk equal to a and k, which is any subsequence, may or may not have a limit. And as an example, consider the following sequence: an equal to minus 1 to the n. And we know that this sequence is 1, minus 1, 1, minus 1, 1, and so on and so forth, so has no limit. If then we consider the subsequence a to n equal to minus 1 to the 2n, well, this subsequence is 1, 1, 1, 1, which clearly is always 1, so tends to 1, has a limit to 1. And if instead we consider a to the 2n plus 1, namely minus 1 raised to the 2n plus 1, what we get is a constant sequence always equal to minus 1, which clearly tends to -1. So with this example, we just saw that if the original sequence has no limit, we can't say anything about the subsequences. Now, there is an important corollary of this theorem, which is the following. Let bk and ck be two subsequences of an with bk that tends to a limit L1 in the extended real line. ck tends to L2 in the extended real line, with L1 different from L2, then we can conclude that an has no limit. The proof of this corollary is quite straightforward, and it is based on contradiction, and it goes like this. So we have a proof. Well, let's assume by contradiction that an tends to a limit L in the extended real line. Then, by the previous theorem, it should be that bk tends to L and also ck tends to L. But this, of course, is impossible because we know that they tend to different limits, so this is a reductio ad absurdum, and this will conclude the proof. Okay, so the only possibility is that the original sequence doesn't have any limit. Now, this corollary is useful. Let's write this. This corollary is useful to prove, to show that a given sequence has no limit. It is sufficient to find two subsequences with different limits. Let me give you an example of this. So, example 1. Let's say that we have the sequence an equal to n to the square plus minus 1 to the n times n to the cube. Okay? And we want to show that this has no limit. We need to find two subsequences, let's say bk and ck, which have different limits, because we know that if this is the case, it is just impossible by the corollary that an has a limit. For example, let's take for bk a to n, only the even indices. So what we get is 2n raised to the square plus minus 1 raised to the 2n times 2n raised to the cube, which is 4n to the square. Now minus 1 to the 2n is 1, so we simply get plus 8n to the cube, and clearly this is something that will diverge to plus infinity. Let's instead take for ckA with the 2n plus 1, which is equal to 2n plus 1 all to the square plus minus 1 raised to the 2n plus 1, and then we have again 2n plus 1 raised to the cube. And let's see, this is 4n to the square plus 4n plus 1. Now minus 1 raised to the odd number is minus, so we get the minus, well, the cube of 2n plus 1, this is 8n to the cube. Then we have 3 times 2n squared, which is 4n squared, so we have 12n squared plus 6n plus 1. And again, this gives 4n to the square plus 4n plus 1 minus 8n to the cube minus 12n squared minus 6n minus 1. And the 2, 1 will cancel, and we are left with the minus 8n to the cube, and then we have minus 8n to the square minus 2n, and clearly this, as n goes to plus infinity, will diverge to minus infinity. So this is a sufficient proof to see that the original sequence an cannot converge. Okay, let's take another example. Example 2. Let's take this sequence an equal to n to the cube plus minus 1 raised to the n times n to the square. And we would like to prove that this will tend to plus infinity. Okay, let's see how can we do this. Well, we can follow 2 approaches. Okay, the first approach would be to use the squeeze theorem somehow, right? So because we have a feeling that this will diverge to plus infinity, we would like to write that an will be larger than or equal something that we see. It is clearly something that will go to plus infinity. And we can just build something which is larger than an by replacing minus 1 to the n with 1, okay? So with the minus 1, sorry. So just considering n to be an odd number. And so that implies that this is clearly larger than or equal n to the cube minus n to the square. But clearly we know that this will diverge. Let me use the other color. This will go to plus infinity because n to the cube is faster approaching plus infinity than minus n to the square approaching minus infinity. So this clearly will go to plus infinity, and by the squeeze theorem we can conclude that an goes to plus infinity. So this is one way. There is another way. So let's see a second approach to calculate this limit. What we could do is factoring out n to the cube. So we have n to the cube here, and this multiplies 1. Then we have plus minus 1 raised to the n divided by n cube times n to the square, which is equal to n to the cube. We have 1, and of course we are just left with the plus minus 1 to the n divided by n. But we clearly see that we can easily conclude that this will tend to 0. Okay, and because this will tend to plus infinity, clearly this we can conclude that this will go to plus infinity. Now, if we are not convinced about the fact that minus 1 to the raised to the n divided by n tends to 0, we can do this. We can just use the green pen here to show this. Okay, let me give a simple proof of this statement. We can certainly say that minus 1 raised to the n, okay, it depends if n is even or odd, but certainly minus 1 to the n is something that is in between minus 1 and plus 1. Now we can divide by n, which is a natural number, so it's positive. So we have minus 1 raised to the n divided by n will be something in between minus 1 to the n and 1 to the n. But we know for a fact that as n goes to infinity, this will go to 0. This will go to 0, and once again, by the squeeze theorem, we can conclude that this goes to 0. Right. And this was another example. Let's give now another example here. And let's call this example 3. Let's consider this sequence. 3 plus sine of pi over 2 times n. Okay, all this raised to the n. Okay, and we want to establish the limit as n goes to infinity. And we can say that this is plus infinity. Why is that? Well, because I immediately realized that this part, of course, will be limited between minus 1 and 1, and instead the 3 basically raised to the n will tend to plus infinity. So we have an intuition that this sequence will be divergent to plus infinity, but we want to prove this, right? So we can say the following. We can say that this is 3 plus somehow we can reuse the squeeze theorem. We can say that 3 plus sine of pi over 2 times n, all raised to the n. We would like to prove that this is larger than or equal something, okay, that will go to plus infinity, and then by the squeeze theorem we will prove the statement. So how can we make something which is larger than this? We know that sine is always something. Now the sine is always something between minus 1 and 1. So to create something which is smaller than this, we would take minus 1 here. So what we have is basically 3 minus 1 to the n, which is to the n, which is 2 to the n. But in fact, we know that this 2 to the n is an exponential. So this will go to plus infinity, and finally we can conclude by the squeeze theorem that also this goes to plus infinity. A totally different behavior can be observed if we replace these 3 with the 2. So let's go with the example 4. Let's study the sequence an equal to 2 plus sine of pi over 2 times n, all raised to the n. And I say that this sequence has no limit. Now, why is that? Let's see this at the level of intuition. Well, if I make the sine equal to 0, what happens is that the sequence will become 2 plus 0 raised to the n. which of course is something that will go to plus infinity, so it will diverge to plus infinity. If instead we make the sign equal to 1, right? So that implies that we get 3 to the n, or better, if we make the sign equal to -1, what we get is that we have 2 minus 1 all raised to some exponent, which is equal to 1 is constantly equal to 1, so that implies that this will tend to +1. So we have now 2 subsequences with a different limit, which implies that the AN sequence, the original sequence, has no limit, okay, by the previous corollary. Okay, now let's try to be more formal. We know what is the way. We want to find now. So let's find 2 subsequences with different limits. Now, because if we go back to the first 2 ideas, now how can we make the sign of pi over 2 times something equal to 0? Well, we know that this happens when the argument of the sign is just a multiple of pi. So we can think of having 2n here, because in this case we would have just a sign of n times pi, which is of course 0. So this seems to be the right choice for the first sequence. So let's say that the first sequence could be a to n, which is 2 plus sine of pi over 2 times 2n, all raised to the 2n, and this is simply 2 raised to the 2n, which is 4 to the n, which will diverge to plus infinity. So we have now a first subsequence. Then we need another subsequence such that the sign of pi over 2 times something, we need to find the specific strictly increasing subsequence of indices, such that this is going to be equal to -1. But if we just remember that the sign is equal to -1 here, so we have -1 when, for which angles? For 3 pi over 2, then we have 7 pi over 2, then we have 11 pi over 2, and so on and so forth. So we can rewrite this sequence as 3 pi over 2. Well, this is just a multiple which we can say is 4n plus 3 times pi over 2. In fact, if we have n equals 0, we get 3 pi over 2. If we have n equal 1, we have 7 pi over 2. If we have n equal 2, we have 11 pi over 2, and so on and so forth. So this seems to be the right choice. Okay, so we have that sign of pi over 2 times 4n plus 3 is always equal to -1. So this is the idea for the other subsequence. So the other subsequence is a 4n plus 3 equal to 2 plus sine of pi over 2 times 4n plus 3, all raised to the 4n plus 3, which is equal to, because we know that at this point this will be equal to minus 1, what we get is 1 raised to the 4n plus 3, which is of course always equal to 1, so this will tend to plus 1, which proves that the original sequence has no limit. Now, this corollary is useful to prove that a sequence has no limits, and this is proved by identifying two subsequences with different limits. Now, a similar theorem is used to prove that a function has no limit, and let's state this theorem. So the idea is pretty much the same, but now we want to prove that a function has no limit by identifying two sequences which take the function to have different limits. So let an and bn be two real sequences such that, first condition, an tends to x0 in the extended real line. So the first sequence tends to a limit x0, which can be finite or infinite, and the second sequence bn tends to x0, the same limit in the extended real line. And again, also this limit can be infinite or finite. The important thing is that these two sequences tend to the same limit. Now, the second condition is that the function f evaluated at the elements of the first sequence, f of an, tends to a limit L1 in the extended real line. Again, this can be finite or infinite. And the function f evaluated at the elements of the other sequence bn tends to a limit L2 in the extended real line, with L1 different from L2. Now, if these two conditions are satisfied, then we can conclude that limit of f of x as x goes to x0 does not exist. And the proof of this is quite straightforward, and it is a proof by contradiction. So let's give the proof. Let's assume that the limit of f of x as x goes to x0 is equal to some L in the extended real line. Then it should be that f of an tends to L in the extended real line, and also f of bn tends to L in the extended real line. But this, of course, is a reductio ad absurdum. So this finally proves by contradiction that it is impossible that the function f has a limit. As an application of this theorem, let's prove that the limit of sine of x as x goes to plus infinity does not exist. Now, by the theorem, let's prove this. It is sufficient to find M20 Sub-sequences AN and BN such that AN tends to plus infinity, Bn tends to plus infinity, and it must also happen that the sign of An tends to some L1 into the extended real line, sign of Bn tends to L2 in the extended real line, with L1 different from L2. Now, if we think about the sine function, well, we can find a sequence an such that the limit is always plus 1. Well, actually, it is constantly equal to plus 1, and another one that is constantly equal to minus 1. So what could that be? Well, for example, we can take, well, if we are looking for a sequence that provides a sign always equal to 1, clearly we are looking at pi over 2, and then we'll have 5 pi over 2 or 9 pi over 2, this sequence. So we can say that if an is equal to pi over 2 plus 2 pi n, well, this sequence is such that the sign of an is constantly equal to plus 1, so clearly this will tend to 1, to plus 1. And instead, if we pick here 3 pi over 2 plus 2 pi n, so if we have Bn equal to 3 pi over 2 plus 2 pi n, clearly we have that the sign of Bn is always equal to minus 1, so this will tend to minus 1. So this is sufficient to prove, by using the previous theorem, that sine of x has no limit as x goes to plus infinity. As another example of application of this theorem, let's consider the function cosine of 1 over x squared, and let's prove that the limit as x goes to 0 plus of this function does not exist. Remember that the behavior of this function is something like this. It is a function that oscillates between minus 1 and 1, and the oscillation will become more and more frequent as we get closer to x equals 0. So if this is the x-axis and this is the y-axis, we know that the oscillation are bounded between minus 1 and 1. Now, we would like to prove that cosine of 1 over x squared has no limit as x goes to 0 plus. So we should find two sequences that have different limit. And one possibility would be, for example, to find a sequence that always pick these elements of the function. Let me say that this sequence is an, and we can find another subsequence that go and pick all these elements where the cosine is equal to 0. Okay, so let me call this Bn. Now let's prove that indeed this cosine of 1 over x squared has no limits. by the theorem, we know that we need to find an that tends to 0 plus, such that f of an tends to some limit L1 into the extended real line. Another sequence Bn that tends to 0 plus, such that f of Bn tends to L2 in the extended real line, and we need to have that L1 is different from L2. Okay. Now, one possibility would be to find an where the cosine is equal to 1. So let's say that the cosine of 1 over an squared, this must be equal to 1, which implies that 1 over an squared, where is the cosine equal to 1? Well, for 1 over an squared equal to 2 pi n, which implies that an would be 1 over 2 pi n on the square root. And we see that the condition that an tends to 0 plus is satisfied. So clearly we can say that f of an is constantly equal to 1. So clearly this f of an tends to 1. Okay, let's now work on the other sequence Bn. We would like to have now that the cosine of 1 over Bn squared is equal to, the cosine has to be equal to 0. And we know that the cosine is equal to 0 when 1 over Bn squared is equal to pi over 2 plus 2 pi n, which implies that Bn would be the square root of 1 over what? We can write 1 over pi over 2 plus 2 pi n. We can rewrite this maybe in a better way, as this is pi times 1/2 plus 2n, and again this can be also rewritten as 2 divided by pi times 1 plus 4n. And we see that also Bn tends to 0 plus, but we have the f of Bn now. This is constantly equal to 0, so clearly tends to 0. And this concludes the proof. Let's consider another example of function with no limit. Example 3. Let's consider this function: sine of logarithm of x plus 1, all multiplied by x. And we want to prove that the limit as x goes to plus infinity does not exist. Okay, now how can we see this? Well, we immediately realize that if we make this sign to be equal to 0, we have a function that will diverge to plus infinity, because if the sign is equal to 0, we just have limit of x as x goes to plus infinity, which is clearly something that will diverge to plus infinity. But if we make sine to be equal to -1, well, we have an undetermined form, 0 times infinity, so we may have a function that will have a different behavior. Okay, so let's see let's see what can we do. Let's see if we can find, okay, if we can find two sequences with different behavior. Now, if we want to have, for example, a sine of the logarithm of an to be equal, so of course, let me make the usual statement. We need to find an that will go to plus infinity and bn that will go to plus infinity, such that f of an will tend to L1 and f of bn will tend to L2, with L1 different from L2. Usual process, okay? Now, an. Well, we want to make sine of the logarithm of an to be equal to 0, but this implies that the logarithm of an, where's the sine equal to 0? Well, at every multiple of pi, okay? So this implies that an will be e to the n pi, and we see that an clearly tends to plus infinity, so this is a good candidate, and we have that f of an in this case is diverging to plus infinity. Good. So one sequence that will make the function diverge. Then let's have a look at the sequence bn such that the sine of the logarithm of bn is equal to -1. Okay, so where is the sine equal to -1? When the logarithm of bn is equal to 3 pi over 2 plus 2 pi n, which implies that bn will be equal to e raised to the 3 pi over 2 plus 2 pi n. And we clearly see that bn is something that will diverge to plus infinity, so this is a good candidate. And what happens now? Well, it happens that f of bn is equal now to what? Well, it will be -1 plus 1, right, times bn. But this function is constantly equal to 0, is always 0, just because the first term is constantly equal to 0. So this is a constant function, always equal to 0, and of course this will tend to 0. And this finally concludes the proof. Let's consider one final example of a function with no limit. Example 4. Let's consider the function 2 plus sine of logarithm of x divided by 5 plus sine of x. So another function that contains the sine and the logarithm, and we want to prove now that the limit as x goes to plus infinity does not exist. So once again we will make use of the theorem, and we would like to find two sequences, okay, with different limit that will take the function to a different limit. And okay, so again we need to find an that will go to plus infinity, bn that will go to plus infinity, and f of an will go to some L1, f of bn will go to some L2, with L1 different from L2. Okay, now playing the same game, we might look at a sequence an such that the sign of the logarithm of an is equal to 0. Let's see what we get. Well, this implies that the logarithm of an, now if the sign is equal to 0, this is happening when logarithm of an is equal to n times pi, which implies that an is equal to e to the n pi, which is certainly a sequence that will diverge to plus infinity. And we have now that f of an, what is the function evaluated at this sequence? This will become 2, because clearly the sign of the logarithm of an is equal to 0. This was the first condition. And we have 2 divided by 5 plus sine of x. So we don't know what is the limit of this, but what we certainly know is that because sine of x is something which is always bounded between -1 and 1, we know that this is always larger than or equal. We need to build now a fraction which is smaller. So we'll keep 2 on top, but we need to increase the denominator, and the max value of the denominator of course is 6, so this is just 1/3, right? So this is to say that if we represent on a line 1/3, well, what we can say is that f of an will be certainly always in this part of the real line. Now let's see what happens if we look for a sequence bn such that the sign of the logarithm of bn is instead equal to -1. Okay, so let's see what happens for this other sequence. Let's make some space here. So this implies that the logarithm of bn, when is the sign equal to -1, where the logarithm of bn is 3 pi over 2 plus 2 pi n, okay, which implies that bn is equal to e raised to the 3 pi over 2 plus 2 pi n, and once again we have that bn clearly is diverging to plus infinity, so this is a good candidate. And if we evaluate the function at bn, what we get now is the following, is that we get 2, the sign is equal to -1, so 2 minus 1 divided by 5 plus sine of bn. So this is 1 divided by 5 plus sine of bn. And we know that this must be less than or equal, so we need now to build a fraction which is larger, so we'll keep the same numerator, and we need to take the minimum possible denominator, which is of course 4, because if sine achieves the value -1, we have 5 minus 1 is 4. So we see then that if we have 1/4 here, let me use a different color, so this is 1/4, we can see that the function f of bn is always bounded by 1/4, and this is clearly a reductio ad absurdum. So that implies that the function evaluated on the two sequences must have a different limit, which concludes the proof.